good morning, everyone. So, take our seats. Thank you. We have our last presentation of the morning, so it's going to last an hour, but we'll get out of here by 12 o'clock so you can go to your class this afternoon. All right, so our next presentation is the school's SAE Baja team. They're going to describe all the work they did this year, more than a year, basically, more than the academic year, designing and building the car.
All right, Baja SAE. So my name is Joseph Moog. I'm the captain this year. I have John, the vice president, Gabe, the treasurer, Leo, the secretary, Christian, shop manager, Brandon, social media manager, Raymond Mitchell, Miguel, Vanessa, Rob, James, and Phil. Go a little faster. So, quick outline, we're going to talk about what Baja SAE is, then we're going to talk about frame, drivetrain, suspension fabrication. This semester we really only did fabrication, not a lot of redesign. Then we'll go over our sponsors, financials, and the club. So, what is Baja SAE? It's one of the largest collegiate design competitions. You're tasked with designing, building, testing, and then racing an off-road vehicle from scratch. Pretty self-explanatory. The competition consists of static and dynamic events. You have the tech inspection, cost event, design, judging, sales presentation, simulates like the business end of the project and engineering end, and then the racing part, the cool part. We got acceleration, hill climb, maneuverability, suspension, and a 4-hour endurance race. This year, June 11th to June 14th, we'll be competing in Palmyra, New York as car number 122.
So as we explained last semester, there's three main subdivisions. We have frame, suspension, and drivetrain. So this time we dealt with fabrication. So I know it's lagging, but I don't know if you remember the last semester. This is basically what we proposed, and this is what we delivered. So how did we go from just regular old tube to the frame chassis of that? Well, there were 4 basic processes. There's tube cutting, there's grinding, there's bending, and then there's welding. So we go on to tube cutting. Essentially, at the beginning, we used a bandsaw, and but essentially we used the bandsaw to cut the tubes. We actually had a cutlass, so we with the tubing, we would sometimes just get small rings of waste, which is much different from before. But after a while, we ended up using a chop saw because it was just much faster. Then for tube notching, we actually used a hole saw, but quickly we found out that this was not very effective, so we just moved on to tube traces and a tube trace and paper clips. We were just notching all winter break long. It was freezing cold, but we got it done. After that, we moved on to tube bending. So we had a hydraulic pump, and essentially this was manual, so as you can see up here, we were actually doing it ourselves. Essentially, this allowed us to get nice clean bends. Compared to last time, they used a different setup, which means they were getting wrinkles in their tube bends, and it was not as nice or clean as this one. And as you can see here in these pictures, we have a couple bends in our car, and this was an essential part of manufacturing. We also have tube welding. So basically, after the notching process and the bending process, everything was joined together. We basically have all the welding that Joe did. Use a little video just to show. I'm sure you guys probably have seen it on the Instagram, or maybe we also will tell the little workshop very soon. But yeah. And then frame fabrication. So essentially, we worked our way up. We worked in planes. We went from the rear rail loop. We started flat, and then we started working our way up. And essentially, that's how we ended up. Usually, just a small view of the front, and then the rear.
If you recall from last semester, my primary focus was on creating a frame jig, which helped us in our manufacturing process. What this frame jig did was pretty much keep every primary component of our chassis coplanar, and the ideal plane that we wanted for fabrication. On the left side of the screen, you can see that is what our model was in SolidWorks. And this was our executed plan in the middle figure and the right figure, and we were able to pretty much manufacture all primary components on our car within 15 thousandths of an inch. Without the jig tolerance. That was the jig tolerance. So in theory, the tolerances for the primary members of the chassis was also 15,000. My scope of work in the second half of the semester sort of shifted to driver safety. So on this slide specifically, the firewall, which protects the driver from the engine components, and also the skid plate, which protects the driver and drivetrain components from kicked up debris, essentially. So basically, very basic process on our manufacturing. We would take cardboard, put it up against our chassis, trace it with a Sharpie, and then we would transfer that trace onto sheet metal, and then use any grinder, metal shears to cut it out. Splash guard and the body panel molds, a very similar process. There's only one extra step. We did have to bend the sheet metal. So we don't have a sheet metal bender. So what we would do is two guys or girl would fix it to the table, and we would just push upwards to get our desired bend. So it was a little janky, but in the end, we got our desired shape.
All right, so next I'll be talking about the body panels. So if you might remember from last semester, I was working on carbon fiber body panels, but just to remind everybody what they do. So they fully enclose the cockpit to protect the driver. So this whole section is where the driver sits, and they're completely surrounded by body panels. And what they do is prevent debris, dirt, and intrusion into the driver compartment so that the driver stays undamaged. And the panels are easily removable for rapid service areas. So let's say we have damage in the front, we can take this panel off, pop it out, fix whatever we need to fix, pop it right back on, we're back in the race. And these are the two designs we have proposed for the body panels, and you'll see how we got to actually making them. So to help with the design, we did an aerodynamic simulation. So it's very rough, but we noticed that in the back here there's a lot of vorticities. So that's why, as you see in figure 36, we have these aero cones in the back to help with the drag and to actually create these body panels. We have a little video here. It's Leo and I. We are making the body panels itself, so we're painting out resin on the carbon fiber. But there are other molds that we had to make that wasn't just a flat panel. So Joe and Brandon, they created these molds. So Joe created this nose one, and then we popped out the panel. Then, as Brandon explained, we put cardboard on the frame, and then we made this mold, and then we have the aero panel molds in the same style, and they were created. And after everything was created, this is the final frame with all the body panels, basically exactly how we added them on.
So you basically need a seat, obviously. This year we actually decided to go custom. So we had to make a mold from scratch. We used foam, cut it with a hot wire provided by Dr. Lusso. Then we used a drill to get the nice contour. We layered a thin coat of compound and then sanded it down manually, as you can see in this picture over here, in order to get nice smooth consistency across. Then we layered 6 layers of carbon fiber, same process as before, and we cut it manually with a grinder to give it a shape. We would have preferred to keep it this way, but we ended up cutting it slim because of the rule book and meeting all the regulations.
Drivetrain, yay. So drivetrain design, if you're unfamiliar, we put the power from the engine to the ground. So I put a little functional diagram of our drivetrain. We have an engine, CVT, transaxle, and our car is 4-wheel drive, and you can see a little drivetrain components there. So we also have a front differential. This year, if you remember from last presentation, we designed it to minimize components and actually be serviceable. So the first component is the engine. We bought a brand new engine, Kohler CH440. We mounted it in the car as low as possible. You can see here. We mounted in the car as low as possible. We used technical drawings to get the hole alignment. That was really annoying to do. We got the holes aligned perfectly, got the engine mounted as low as possible. It's also easily removable this year compared to previous years. You used to have to take the whole car apart to get the engine out. Now you can just slide out the side. And then the rule book says that you have to have a certain amount of exhaust clearance. So we made sure that our engine is mounted in a way that we have the proper clearance for the exhaust. After the engine is the CVT. We have a CV Tech CVT. Spacing and alignment super important. Many previous years we just not have the CVT lines and we slip a lot. So we got the technical drawing, where's the laser? We got the technical drawing from CV Tech, and then we used a laser cut jig and machined PVC spacer to get the center to center distance of the CVT correct and the offset of the CVT correct. You can see the CVT mounted up there. Oh, the pictures get bigger. Oh yeah, you can see CVT operation. Next is the transaxle. So this is the main power units, the main gear reduction. Distributes power to the two rear wheels. We had to mount it via two plates. So we laser cut wooden spacers to get the hole alignment correct. It's mounted with 12 bolts, 6 on each side. If you can see here, this is pretty nice engineering. You can see the CAD, you can see the real one, the same. That's good. So we mounted it up to spec with the CAD, came out good, very tight tolerances between the parts.
All right, boom, we got the shifter. I made the shifter. As you can see, we have a brand new, laser pointer working. We have a brand new shifter design because the last one sucked, according to some people. It's using cables. Here it is mounted in the car. It's pretty simple, just 2 cables for the shifter to actuate the transaxle, 1 cable for the locker to actuate the rear differential locker. Right now it's fully 3D printed. It will be fully 3D printed except for the shifter rods you see here, and through the power and glory of Dr. Caluso, we are currently milling them out of aluminum. But yeah, it's fine. Anyways.
Doesn't work right now, but it's in progress. Next, right angle gearbox. So in order to have 4-wheel drive, we have a right angle gearbox. Pretty simple. Power comes in, comes out at a right angle. So you can see the CAD that we had from last semester, mounting, identical, which is good. And then we have a little diagram of all the ways that the axles spin. It's very important that you have the front wheels and the rear wheels spin in the same direction. Next, from the right angle gearbox, we have a drive shaft. You can see our CAD from last semester of the drive shaft. And then you can see a PVC mock-up of the drive shaft. This was very, very annoying to do because every single orientation of this drive shaft hit a frame member. So we had to keep mocking it up, but we got it figured out. Then in order to actually have the drive shaft connect to drivetrain components, Christian's going to talk about machining some parts.
So we had to make some custom drive shaft ends. Now, to get a custom drive shaft made and balanced costs a lot of time and money. We only got so much time. So we have to make some ends. As you can see, here's the process. Click, click, click. For one of them, we did buy a pinion gear, chopped it in half. It was a little rudimentary what we did. We had to take off the heat treating, as you can see, and then machine it down to our final spec. Don't worry about this glowing blob of metal. We did have to build up some of the shafts with weld in order to machine them down, but turned down on the lathe in the shop, brought down to a tolerance plus minus 0.3 of a thousand. That's 1/10 the thickness of a human hair, and they're heat shrink fit. As you can see in this video, you heat up the drive shaft, you cool down the end, and it just slips right in, and it's a friction fit. And we weld it just for extra safety. Next.
Yeah, so talking about welding, I took those drive shaft ends that looked really pretty and hammered them into the end of the drive shaft and welded the crap out of them to make sure that they would be strong. So in order to get around connecting a spline shaft to the drive shaft to connect to a keyed shaft on the gearbox, we got creative. Christian made those ends, put them into the drive shaft, and then you can see all the fabrication there. You can see it on the car there. So we were able to get around the drive shaft. Pretty challenging to make, but it came out good.
So in order for the drive shaft to connect the right angle gearbox to the front differential, so the power can get from the right angle gearbox to the front differential to allow 4-wheel drive, we used a bearing to support the drive shaft as well as a U-joint to connect the 2 drive shaft segments. Both of them are located behind the firewall, which allows the drive shaft to not hit any of the seat support members. There, in figure D50 is a picture of the bearing. The bearing can withstand loads and rotational speeds much higher than what a hog will be using. And it was pretty cheap, only about $13. And figure D51 is the U-joint connecting the 2 drive shaft segments together. We found that U-joint on the MasterCard. I also designed CV axle sleeves to purpose of these CV axle sleeves is so that our end have a custom length CV axles. The CV axles we bought were not the appropriate length, so we cut them, and then we ordered a tube which we use for the CV axle to connect them. The CV axles have 1.25 inch outer diameter and 3/4 inch inner diameter, and made of AISI 4130 steel. It's designed to have 1 inch inner diameter, but because of the CV axle components in the front, we had to order a 3/4 inch inner diameter, and then Christian machined the ends to have 1 inch inner diameter.
All right, next, front diff. It's just a front diff, pretty explanatory. But we had a different front diff left over from previous year that was limited slip here, but then I found that you can get a smaller one, so I got a smaller one. So same deal as everything else. We just mounted it in the car. Has a 3.82 to 1 ratio. Not that that means anything to anyone here. And then it's engaged via a button on the steering wheel. So since it's LSD, you click a button on the steering wheel, and then you're in 4-wheel drive. As per the rule book for SAE, you have to guard everything that rotates. So this was annoying. So you can see here, we made a guard for the U-joint on the front diff. Had to use a lot of clamps to put it on, then weld it, then grind it, then mount it. It came out pretty nice. And then this is in progress right now. We're guarding up the drive shaft. So if the drive shaft was to fail, you have some hoops here to prevent it from flopping around and hitting somebody. Another powertrain guard is the CVT guard. This is pretty cool fabrication. We cut this long piece of metal as per our CAD, then used the press with Big Al, our mascot, a big aluminum cylinder, to press it into circles. Then it wasn't straight whatsoever, so we tried to clamp it and that didn't work. So then I brought an anvil here and we just hit it on the anvil until it was straight. So I think you can see that process there. Just cold rolled it on the anvil for like a couple hours and then it was straight. It looks really nice. So there's the CVT cover. We're still going to cut vent holes to vent the CVT, but that brings us up to the rule book spec of covering everything that rotates. Everything's flagging a little bit.
So in order for the car to actually move, we have 3 components. We have the gas pedal, the throttle cable, and then we have the bracket that connects it to the actual engine. So we fabricated the gas pedal by using 0.188 inch steel, and then we welded that together. We connected that to a 71 inch throttle cable, which had the proper tension in order for the cable to actually pull on the bracket system that's connected to the engine. Essentially, that just lets the car go forward. And then we have a spring to return the gas pedal to its original position once your foot is off the pedal. So now just to get into the hubs, they were redesigned. We ended up moving away from our fully custom hub design just because it takes too long to get it, because of lead times. It was too costly, and then also it was just easier to manufacture it ourselves. So we modified our Sportsman hub, and then we did some testing on it to make sure that it would handle any dynamic or static loads by doing brake test, exhaust test, and also a foot test.
So making the hubs. Thank you, Dr. Puso, for helping us with the entire process, basically. We turned down the outer diameter of the hub to fit inside the rim. Then Miguel machined down the face of the hub to clear the brake caliper. You can see the brake caliper there, so we shaved that down. I don't know if that video plays, but it was a time lapse of machining it. And then in order to actually mount the brake rotors onto the hubs, we had to machine flats. So we wrote a DXF file to program the Tormac mill to put 4 holes and 4 flats up to our CAD drawing there. You can see Miguel doing it. 4 flats, which then mount the brake rotors. You can see that mounted there. We have the proper clearance, and it fits in the rim, which is good.
All right, so I did the brakes. That was the CAD model that we had from last semester. Joe called me up, he said it's trash. I had to change it. So pretty much all I did was turn it around. The reason it was trash is because it didn't fit in the toe box, not really, but like our foot was like bent up like this. So all I did, as you can see in the figure on the right, was just turn it around. And that's the final assembly. We did this all by hand from scratch. So that's why there's a line. I am Semcut Sen. If anybody doesn't know what Semcut Sen is, like a laser cutting company that cuts metal. I did that all by hand because I'm a genius. I did that. It's really good. It's lagging. The rotors, however, they were Semcut Sen. I I cannot do that. So as you can see from the figure on the left, that's the rotors that we got from the front and the rears. That's also me machining the standoffs because we had to connect the standoffs to the rotors. So I machined them down. They all had to be the exact length because when they're not, the rotor wobbles. So, and then we assembled them in the car. No super. That's pretty much what we did.
And then I did the brake lines. So just like a regular car, we decided to copy it. Regular cars use rigid tubing. Basically, you buy a roll like this. They make them also in stainless steel, but that sucks to work with. So we went with nickel copper combination. And you roll it out, straighten it, you bend it to how you want it, as you can see here. Obviously, you have to know everything that you need for it, so I did a nice little takeoff chart. And then you put them in the car. Just around a picture of it, but after they go up to the frame from the master cylinder, you have a flex line because obviously, and you see, obviously the wheel turns and it moves and stuff like that. You don't want a rigid tube on that. So from the frame to the wheel, flexible line. From the frame to the caliper, from the frame to the master cylinder, rigid line. Oh, we'll get some electrical components in the car. Most important one, you gotta have it, is the kill switches. These didn't take that long, few revisions. Carbon fiber body, has to have graded hardware, all that good stuff. And there's 2 of them mounted on the car, as well as powering everything. We got 2 batteries this time, compared to last time, because last time the battery was so heavy. So this one, I kid you not, is 1.5 pounds. And we also have a backup battery. This is a Bauer battery. It's the same tool battery, it's the same battery that our power tools use. All you have to do is quick disconnect from the car. Not only does it charge this battery, which powers everything, it's quick disconnect. No more charging the car, no more relying off the cables, everything's isolated. Beyond that, we also have a dashboard. Last year's dashboard, it was alright, but this one's better. It has our logo on it, and it's circular. That's really it. Like I said, we have tachometer, speedometer, gear selector, all that good backup camera. I'm saying all that good stuff. This is definitely done willingly by a computer science major. Yep.
So to actually have the batteries in the car, we needed a battery mount. At first, we tried to put both batteries in the one mount. Unfortunately, there wasn't enough room in the toe box, so Leo took over and created 2 separate mounts.
Yeah, so when we were testing the first battery mount, we realized it wasn't fit in the toe box. So Christian was insistent that we keep it in the toe box. We could move it to the rear and make our lives easier, but no. So I had to basically split it into 2 components, one for the rechargeable battery, one for the LiPo battery. And we managed to get it done in 1 iteration. Not just everything. It took like 15 minutes. Anyways, we mounted it. As you can see, this is your POV from inside the car. You can see you can reach it easily. You need to swap out the battery, just quick snap out and snap back in. And this is where the LiPo battery would go. It's mounted. It's like rigid, so it won't like fall off during just normal use.
Alright, so moving on to the suspension, we dealt with everything that had to do with the handling, ride quality, and feel of the vehicle. So to start off, the first thing we manufactured was the A-arms. So we started off by comparing our technical drawings and using the fixture table to ensure symmetry and accuracy to our technical drawings. So while doing this, we made sure that the upper A-arms were set to an overall length of 12 inches and a width, the widest part of 8 inches center to center, while the lower was 14.5 inches length and 10 inches center to center for the width. As you see in figure S-1 with all the fixtures and the side-by-side technical drawing. And then figure S-2, we have our first full set of A-arms all welded up. And then after they were all welded up, we had to add some more components to them. So the first of those components was the upper A-arm plate, which was used for mounting the shock tabs to the upper A-arms, just to get some more surface area and help with those stresses coming from the shock absorbers. And then we also needed to add to the end of the A-arms the weld nuts, the lock nuts or game nuts, and the super spool rod ends, which are used for the connection to the front nuts. Then on the opposite side of the A-arm, for the frame side, we had to make our bushings. So we use Delrin and steel crush and steel stock to make our bushing components. So first was the Delrin bushings. We used the CNC lathe in the manufacturing lab to turn down the outer diameter to 0.981 inches, cut the length to 2 inches, and give an inner diameter of 5/8 inch. And then the steel crushing sleeves were the similar process, except now they have 5/8 OD, cuts at 2 1/8 inch, and a length of an inner diameter of 1/2 inch. So then once these bushing components were all machined, we had to use the arbor press in the shop to press the Delrin into the A-arm steel. So this is a friction fit, keeps it stationary. And then while the steel crushing sleeves are done, they fit loosely into the Delrin. And this allows for full rotation without any rubbing or interruption around the steel sleeve. And then for mounting, we put the tabs, washers, and bolts all on, and you can see that they actually press against the crushing sleeve, not the Delrin. So this reduces any interference and interruptions in the articulation of the suspension assembly.
So to continue with the custom making components and everything, we decided to design our own steering wheel. So I designed a steering wheel in CAD as well as a mold to go with it. We went with a flat bottom yoke style design, so we have the benefits of a full steering wheel, but we still have the clearance on the bottom for the driver comfort, as well as when we need to get out of the vehicle within a certain time limit, we still have the space. What I did was that I modeled it in CAD, I made the mold in CAD, and we 3D printed the mold and glued it together. As you can see in figure S-11, we used a whole kilogram of PET G, again, that you don't have to design. And we also made a steel an aluminum insert for the core of the steering wheel, so we can have rigidity around where the steering wheel actually holds to the critical spring. So this method of manufacturing with carbon fiber is called carbon fiber molding. So the way how you do it is that you take pieces of carbon fiber and you fill a cavity or a mold, and you basically fill it with resin. So that's what I did here, where we prep all the carbon fiber sheets, which is the same material that we use for the body panels. We cut it into small, manageable pieces. We used all the small pieces and basically a lot of resin, and filled the mold until we got it to about either the height where we had the wall for port, or we overfilled it because we're actually compressing all of the carbon fiber resin into it so that it fills all of the cavities and all the air inside the mold escapes when you actually put it.
All right, so one of the things that we also had to do was revisit our steering calculations, because it's important that the car turns. So sadly, we had to do some math this semester. So this is just a graph of the wheel angle versus the turning radius. So if anybody can picture a car turning in their head, the inside wheel turns on a smaller circle than the outside wheel, so the angle on the inside wheel needs to be sharper. So this is just a graph of the turning radius versus the inside wheel and the outside wheel angle. Right, so we wanted a smaller turning radius, so let's say 9 feet, which is actually really good for a Baja car. It ranges usually from 8 to 10. Just so everybody knows, last year's car was like 25. That car did not turn. Okay, so we wanted to make sure the car turned. So pretty much all you do is look at this graph, 9 feet, you go to 9 feet, which is, it's in inches, it's fine, multiply it by 12, whatever, and go up and you get the wheel angle. So inside wheel is 40 degrees, outside wheel is 27 degrees. And the way this works is the way this does is a geometry called Ackerman steering geometry. And all this means is that the inside wheel gains leverage faster than the outside wheel, so it turns sharper. We had to test this. So this is, the first picture is a picture of what Ackerman steering geometry, so that's 100% Ackerman. Now what that means is that where the tie rod is mounted to the kingpin on the thing, the pivot point of the wheel, and if it lines at the rear diff, that's 100% Ackerman. Now, I'm only going to be talking about Pro Ackerman because this goes a little bit deeper. This is like crazy stuff. But everything in front of it is in percentages. So the picture on the right, that's about 40% Ackerman. So you have to test Ackerman in increments. So I tested like 40, 60, 80, 100, and tested all the wheel angles. And I did that by making this CAD model of a fake steering rack and pushing out the wheels and seeing what the angle is in increments of every single wheel. And I'll show that in this graph. It'll pop up now. All right, so before I talk about the outside wheel angle and inside wheel angle. There's something called dynamic tone. Now, to make it more legible, on a graph instead of having all these lines. Dynamic toe is just the difference of the outside wheel angle, or no, the difference between the inside wheel angle and the outside wheel angle. So you just subtract the two. And then at each Ackerman testing that geometry, we get this graph. Now, I said before that we needed 40 degrees on the inside wheel and 27 degrees on the inside wheel, or that side wheel. And that is black line is the ideal. So this hits two Ackerman percentages, 50% and 40%. So we went with 50%. And the reason is because it fit in the rim, because the other one did not fit in the rim and hit everything. And it followed the calculations, so that's what we went. And then we made it. That's it in the toe box. That's everything we made. We made a tie rod, we mounted it in the toe box. I just want to say, the car steers amazing. We tested it. We were doing drifts in the parking lot. It was great. I'm proud of it. So, yeah.
So the last design for the front knuckle was that we were planning on making it a billet window, where you basically take all window stock and see it down to whatever design that you give a company. Unfortunately, we didn't go with this idea because it would have taken too long and it was very expensive compared to the new design, which is now we made it out of plate steel. So it's basically a bunch of puzzle pieces that get essentially welded around the core. This steel core was machined by our wonderful friend, Joe Messina at Graph Ollie. He was one of the previous members of Baja back in 2012, 2011. And so this is the design that we went with. It was much quicker. We used Sencut Sen, where they cut and bent all of the plates for the steel knuckle. And we also created a 3D printed jig, so that we can have all the plates aligned properly as intended. Unfortunately, with the first iteration, it did not go well. The knuckle that's being passed around now did not have the proper, bolt hole placement for the upper and lower control arms. So I had to revamp most of the design so that we can make sure that there wasn't any interference between the super spool rod ends that were on control arms and the rim itself. But we remade those, sent them back to Sencut Sen. In about a week or two, we had the new knuckles that worked perfectly and basically finalized most of the front of the car.
Alright, so while the iterations were going through for the front knuckles, we started assembling the front suspension assembly piece by piece. So the first thing we did was mount the A-arms. So we did that with the tabs all attached, and then we were able to place it in accordance with our technical drawings, and then measure from the front to make sure we were symmetric on either side of the car. And then we just would repeat the process for the upper and lower. And then while we were doing this, we checked each knuckle iteration with a 3D print to make sure we still had proper articulation and turning without too much interference inside of the rim, with the A-arms, with the rod ends, whatever the hit. We had to check everything. So then after the A-arms were mounted, we had to mount the shocks. So the way we did this was we mounted the upper A-arm first on that plate. We made sure it was normal to it, and then put the shock tabs and everything on the upper part of the shock. And then we looked to see where it intersected with the nose tube on the front of the car, and that's where we welded on. And then we made sure that we had the proper stance, proper ride height, and again, throughout all this, checking the knuckle iterations as we went. And finally, once the knuckle iteration was complete and we had the first welded model, we were able to put it on the right tire, that right picture. That's the first time we had the proper knuckle on the car, and we're able to kind of put some weight on the tires and see how the suspension kind of had that static look. And then once we had everything all sorted out, we were able to put in a little time lapse of putting all the suspension components on. So just kind of let this play through, but it's just, full time lapse of putting all the components on. It's like 5 bolts to seal up the holes, one suspension assembly, so kind of nice and easy to manufacture, put back together and off. And now the next steps are to test and then manufacture spare parts, because we really hope to be able to participate in the suspension interaction test competition, which is really rigorous. And then finally, here's just a front view of our finally completed front suspension setup. And now I'm going to pass it off to Rob to talk a little bit about the rear.
All right. So yeah, moving to the rear of the car, it's a little bit simpler as the rear doesn't steer, so it's a more simpler design. Based off our SolidWorks drawings from last semester, we were able to set up a jig using the different fixtures in the welding table. You can see in figure 39, 40, and 41 some different views of the setup. So yeah, after all the tubes were prepped and measured correctly, we started to weld. You can see in that GIF, Joe, welder, he's just making sure he gets every angle correctly, and in the order really mattered because there was a lot of tight welds that he had to reach. Sorry about that. And yeah, we had to make sure that the arm was stable, so we used fixtures again, and we would avoid warping or distortion. Yeah, so that's the inside and outside view. We made sure to tack it and then remeasure and then fully weld it after. To support the trailing arm, which would be attached to the rear of the frame, we made sure to make rear links, which will be shown next. All right, so over here are the two rear links. Pretty simple, just a straight tube, just cut at a certain length. And yeah, after setting up the tabs on the frame, the rear setup was complete, and we attached all the ball joint rod ends, the bolts, the nuts, and the rear suspension was ready for a shock. So the shock placement was something that's very important, and we wanted to get the most force possible so that we could actually, absorb a lot of force if we're taking big jumps or going over obstacles.
Of course, the rear also has to have its own knuckle design of its own. It's much simpler compared to the front. The rear also had the steel plate design, where just multiple pieces welded around the steel core. We used the 3D printed jig as this one as well to make sure all the plates lined up properly and make sure all of the mounting positions compared, like relative to the trailing arm, was how we had it in the attic.
And then and then you just kind of get the final rear assembly. You can see the two shocks. We got a pretty, I guess you could say, steep angle, but it is rigorously held by this plate right here between the two members, and hopefully we can compete well in the suspension test this year.
All right, this might play, might not. This is supposed to be a build video of just a whole bunch of stuff. As you can see, we just kind of information dumped this, but we built like a lot of parts. If this doesn't work, we're just gonna skip it, it'll be posted later. Nah, give like 2 seconds, otherwise we're gonna keep moving. We're gonna keep moving. You don't wanna watch a 5-minute video of me welding a million different things. So, just go to the next slide.
Yeah, so we don't just build a car, there's actually a lot of other things. So with SAE Baja, there's a lot of other things you need to do to get to comp. So there's a request for proposal, there's roll cage documentation package, there's a cost reduction report, there's a virtual business presentation, an online cost prototype, and design review briefing. So the first couple items are like 20-page things we have to do. If you're not submitting these, we don't compete. And this is me and Raymond here. It's a very accurate depiction of me on the left and Raymond on the right. We're actually tweaking out over the business presentation. We took like a week and several hours on this just to do very great. But, so shout out Gabe, that's me. I wrote the request for proposal, which actually got us to the next round for the virtual business presentation. That's actually the first time our school's ever gotten there. And then shout out Leo for doing the online cost report. This is literally every single nut and bolt, every single process, every single item on the car was documented and cost on the report. It's up. And then, we can't build this car with just ourselves, so we have a couple of our sponsors here that we got this semester, and then these are all our sponsors that we've gotten over the past year. So we're thank you to everybody. And now, comparing our budget from last semester to this semester. Last semester we weren't building anything, so we really didn't spend much. But this semester you can see that we basically spent almost all of our money with 17% remaining. Sounds like a lot, but if you know the actual number, you can decide for yourself. But Joe spent the most money. I'm not surprised, but yeah, that's all right.
All right, besides just being a senior design project, we're also a club. So I think last week we hosted a welding workshop. I taught 30 underclassmen how to run a MIG welder. I think it was pretty cool. Got like the theoretical knowledge from class to a hands-on activity. And then Christian also ran a bake sale, and you can see Christian and Raymond with a lot of money from the bake sale. On other random notes, we brought the car to Mech E-Day, if you remember, so I wanted to include this slide to thank Dr. Booth and Dr. Shibori for letting us do it. If you were wondering how we got there, this was the stages. We went onto the loading dock and then checked for clearance, and then ran in there, we took off the car, put it in the elevator, and got on the floor. So, brought the car to Mech E-Day. A couple acknowledgements. So, a lot of people helped us with this project. We'd like to thank our advisor, Dr. Aravandi. We'd like to thank Dr. Busso. Almost everything that was machined, we talked to him. I think we drove him a little crazy. Dr. Shibori for getting the welding table, Dr. Mansour for some design advice, the dean, mechanical engineering department, Kathy for placing a lot of our orders, Nicole and student engagement for placing orders, Anissa Latif and admissions. A lot of those videos you see online are from them. And then we have a very tight Baja alumni network, so they were able to help us out a lot. So challenges. We thought we should include this because we had some challenges. So a lot of items did not come when they were supposed to come. Like the writing of gearbox you saw, we were supposed to get it in December. We didn't get it. I had to call another company and get a different one. Steering rack took like 3 months to arrive. We had like lots of parts getting here on time, supply chain issues. Sheet metal working, Brennan talked a little bit. We don't have a sheet metal vendor, so everything was just bent on the welding table by brute force. As we were building stuff, the frame was probably the hardest thing to build, but Leo had a crazy CAD plan, so it went pretty smooth. But then after the frame, slowly things were being done what we call live with cardboard. So it slowed us down a little bit. Mother Nature, we worked, I think, every single break that we had, and it was like below freezing for the entire winter break. So it was really, really cold while we were trying to work on the car. Rule book requirements, as Leo mentioned, there's a big 130-page rule book. It was like constant problems with this rule book. It's like reading like a law document, it's horrible. And then previous years, like a lot of the information wasn't like fully written down or recorded from previous years, so we had to figure out a lot of stuff as we went. And then one of our main problems was Christian. We deal with him constantly. All right, future plans. We would have included testing in this. If you saw online, we were driving on Sunday. We were actually driving pretty good. We drove to the quad, and then we started testing it in the lot. And we were drifting around, driving it. And then I was like, okay, let's start taking measurements. And so I was driving to take measurements, and if you're familiar with like tacking one together, it's like a little dot of metal holding something. The whole steering system was actually only tacked together. And I hit a pothole going like 20 miles an hour, and the steering arm like fell off, so we couldn't actually like record all the testing that we were going to do. So our future plans are, we have a design review briefing, so that's a document we submit to SAE showing all the design work on the engineering side we do is worth like 150 points out of 1,000 in the competition. Christian still has to wire the car and do the shifter, so hopefully that gets done eventually. The braking system also needs to be finalized. You have to get all the lines on so the car actually stops. And then testing. Since the competition is June 11th, we have like quite a bit of time. We're going to test the car like crazy. Hopefully find out every weak link so we don't have issues at the competition. We have to do a final rule book check. We'll probably lose our minds a few more times. We're going to paint it, hopefully, and then we're going to race. So that's our future plan for this. I think this might be it. We got some silly pictures here of things that happened. This is how we made, this is our tolerance quality control guy. Baja after hours, cutting, grinding, doing some CAD. Interesting welding positions. I have no idea what's going on there. We have barbecues, heat gun, whatever. And I think that's it. I think we just information dumped you guys. We made a lot of parts. We didn't really know exactly what to talk about. So we just went through a whole bunch of things we made. So if anyone's got questions, we're more than happy to answer them. You can see CAD next to the real car. We were pretty accurate to the CAD, which was pretty good on the engineering side. So that's it.
Questions for the group? We have about 5-10 minutes. Yes, Richard, kick us off.
Compared from from year to year, how much does the competition actually change, or is it pretty much?
So the question was, from year to year, how much does the competition actually change? Repeat the question.
Yeah, so the competition, the events are usually the same. So you always have acceleration, a brake check, a hill climb or a sled pull, a maneuverability, a 4-hour endurance race. So the events are the same, but the location changes year to year, so the actual track is like different. So some years, like John was talking a little how we're gonna make spare parts for suspension. Our school just never attempts suspension because they just like dump like boulders and they have you drive over them, or they dump like concrete barricades. And that like event changes, but it's always super, super rough. So the events, same events, but different locations. So like the actual where you're driving on the ground, the course is different. Does that sort of answer your question? What's up?
You mentioned how the braking systems
Yeah. The steering broke off. Oh, we weren't going that fast. Like we were like going in straight lines, and I hit a pothole, and then the steering, like what's called the tie rod, what mounts to the knuckle. A lot of jargon words here, but the tack broke off. So then all of a sudden the wheel just went like that, and I stopped. And then the braking system, what has to be finalized is all the parts are in there, but you have to run like brake lines because the braking system is a hydraulic system. So you have to run brake lines to the brake calipers so you actually can stop. We're only running with front brakes right now. It's a little sketchy. What's up?
So, from last year's bill, I'm sure a lot of things probably went wrong. Did you guys take that into consideration for this year's club?
Oh yeah, so last year's car, in the nicest way possible, did not perform well at all. So as Ray was saying, the turning radius was large, the car was big, heavy, slow. It went like, I think like 12 miles an hour, 18 miles an hour. So we took like all the things that I knew and we talked to the team, like big, slow, didn't steer, didn't stop, didn't go over bumps. Basically everything the car should do, didn't do super well. So we took all that into consideration, and like this is like a complete redesign. I don't even think we reused any parts from the previous year. Like I think everything's brand new, fabricated for this year. So we're hoping that now the car steers tighter, which from our test, you would have seen the build video. The car steers super tight. We're drifting around poles. The suspension's a lot smoother. The car should go a lot faster. So like we just took everything and hopefully made it all better. So yeah. That's a good question. That's what I was supposed to be testing before I broke the thing. I had a GPS in my pocket for the first test, and it said 22, but we were under the train trestle. And then I did another test and it said 33, so I don't think either one's accurate. Theoretically, the car's supposed to go 30 miles an hour. So I'm pretty confident it's going to go 30 miles an hour. Like when you hit the gas or pulled the string that was connected to the gas, you really like felt it accelerate. It wasn't like laggy at all. So this weekend, I think we're going to test it a whole bunch and we'll try to get a top speed reading. I'm hoping 30 miles an hour. Like theoretical and real is the same. Any other questions? I know I just information dumped you guys at a million like things we fabricated.
Right. You said that you're gonna bring some spares parts for the suspension. You guys can, if the car breaks during the test, you guys can rebuild it and try again?
Yeah, so if anything fails, you can like pull off, go to your paddock, which is like your pit, and you can repair whatever you want, and you just have to get re-inspected. So what a lot of teams that are like good at this do is they make like all the suspension components, they make spare ones. So if you jump like a 5-foot jump and then this just snaps right in half, instead of being like, oh, the race is over, they just unbolt and put a new one on. So actually I was in Maryland with Christian last year, and like the suspension arm snapped in half, like 30 minutes into an endurance race, 4 hours snapped in half, and I had to weld it back together, so we lost like 2 hours mid-race. This year we're hoping to make like a ton of spare components, so whatever breaks, I'm not fixing it. I'm just unbolting it, put a new one on, and send it back in the race.
And we welded it in the middle of the field, and it was red hot, and we had to put it back together. I had a bottle of Gatorade, that's all I had. The guy was like, are you going back in or are you fueling up? He didn't even ask to inspect. We're going back in, went back in, finished the race. Easy.
So yeah, spare parts are important. If you think about your car, things have to get replaced. There's going to be weak links on this, so we're hoping to test it a lot, but then we'll have the spare parts anyway. Like that knuckle that was passed around, I actually had 2 sets of those, the A-arms. We have like 2 of everything. Any other questions, comments, concerns? What's up, Sean?
Who's driving?
The most popular question. I don't know. We're gonna test the car a bunch, and based on like testing, probably pick the drivers. You're a little limited, as I said, like between last year and this year. Last year's car was designed for like a 6'2" guy, and it's really uncomfortable somehow still. This car was designed like a lot smaller. So rule book wise, you have to have what's called driver clearance if you were to roll over, which a lot of cars roll over. So you can't have like an enormous person in the car. No offense to some of our teammates. But like we have to make sure that whoever is going to drive passes like the driver clearance, and then we also want to test with everyone driving, see who handles the car the best, because it's kind of like you got to understand the car a little bit to be able to drive it. It's got quirks and features. Definitely not Christian.
I will be driving my car.
All right, any other questions?
Yes, Jason.
What was the biggest problem with Christian?
Christian's good. He does stuff. Just if you need it done, it'll be done a month after it's supposed to be done. That's the best way I can put it.
All right, any other questions for the group?
Net zero. Some people are net negative.
We have Paul from Electrical Engineering has a question.
Yes, Paul.
I have an electrical engineering question.
You can ask me, I'm the electrician on the car.
Okay, more so, how are you running the dashboard? Are you just using like a Raspberry Pi to connect to it?
We're using an ESP32 LVDS dashboard. Basically, it's all in one unit, and all we have to do is send our signals to it. So it's running a custom program, and we're just sending our signals. We have a tachometer signal, which is just a square wave. We have our speedometer signal, which is also a square wave, just a lot slower, so we're using a Hall effect sensor for that. And then we have our gear selector, so it's going to be limit switches, just literally just if this then that statements. If we get a GPS module, we'll have a lap timer, but it's literally just ESP32 base. I think running off of Arduino IDE. Yep.
Thank you.
Noah, last question.
Just curious, how would you bring it to competition? Do you have to break it down and build it there, or are you gonna bring it home?
How do you bring it to competition? Do you break it down?
No, I'm gonna rent a truck. Last year, I packed it in the athlete's van, unbeknownst to them. But this year, we're gonna put it in a box truck. So you just like drive it into, you think of like a U-Haul. We're just gonna put it in a U-Haul and then drive it there, yeah.
You literally drive onto a field and roll your car out, and that's where you station. So.
All right, let's thank the group. Great job.
All right, thank you very much. Those of you again in MEC 401 or 402 who need to be counted for attendance, Richard, do you mind collecting them? Yeah. Richard's going to collect them again. We're going to restart presentations at 2 p.m. in this room. 2 p.m.